Okay, so for this guy here, this is an actual AP exam question. Like I said, this is a 2017, so very recent, number 2. And we'll talk about how number 2 affects the grading in just a little bit. But what I want to focus on here is we're going to take a slightly different look at this. Okay, see what you think about this activity. What I have for us is I have an actual student's response. Like, what did somebody actually say? And we're going to guess. This is just problem number 2, and we have 3 different ones. I wanted to look at number C first. And we're going to try to guess what their score would have been. Okay? And then we'll go through and we'll talk about the actual scoring requirements. So, go ahead. This is the first part. This is A. Give you a second to read through it. And by the way, you're going to see a lot of, whenever we do this, there are some really interesting folks that just take the decimals out to redonkulous levels. As long as you go to 4, you're fine. If you want to keep going, well, that's just overkill, but all right. Go ahead and read through that, and I'll show you the second part. What work they did versus what work you did. Is their work even correct? I don't know. Okay, so that's A. And take a look at B. And what you'll see here, let me give you a full view of the whole page. This is actually the amount of space and the page that was given to the students for that question. So you're always given plenty of space. All right, when we're doing these, the grades for each individual question will go either from 0 through 4. 4 being the best, obviously. 0 being, oh dear Lord, you left the page blank. Or you drew a unicorn, you get a 0. Sorry guys, you won't get points for drawing pretty pictures. But what score do you think this guy deserves? Or this girl? I hear 2 from Deo. 2. Raise your hand if you think 2. Okay, what about 3? Or 1? I'll tell you straight up, that number, those numbers are correct. And the final answer down here is correct. So those are the right numbers. And you guys are actually right on. This is a 2 problem. They scored a 2. Okay, let's take a look at that one. And then let's see here. Do I want B or A to look at? I think I like A. If I can find where I put it. Too many pages. Here it is. Okay. Here's another one. No, it is not graded on handwriting. Wouldn't that be fun? Looks like they were writing on like lined paper. It's so clear. This is their first piece. A lot of weird tisking sounds. Get the general idea of what they have here? Yeah? Okay. And then this is their answer to the final portion. Is it emotional for you? Is that why we're sniffling? Just nod and smile. It's okay. You were the one that went... So like you're just, yeah, he's okay. I still remember the day after the kids took this test, they all came back and they were like, "Do you fill your water cups with soda?" It became the big thing. Everyone's like, "Panera, yes, yes, we do." Horrible children. All right, so with that, looking at all that information, what score do you think this student deserves? 3, so we're doing an improvement from the last one. Okay, Deo is just very hard to please. Why are you saying 3 and not 4? Okay, so he's got a very good point. They do not have a formula. They do not state what Z star is. The thing about this problem, and it's important to note that this is a problem number 2. As you go through the problems, what they're looking for in the questions get more and more specific. For this problem, what we call it the nature and scope. What are they trying to get you to show, and how broadly or how deep do you have to show your understanding of it? The goal of this was to get to this answer here and to get to these numbers here. Each of those numbers themselves, if they are correct, would get you 1 point. Okay? Then it comes down to what else were they expecting to see. This part A actually counts as 3 pieces to the problem. This is 3 pieces. This is 1 piece. If you get that correct, then that's all you need. They like to see the backup of the numbers so that you can justify where these things came from. So if you were off by a couple of cents on this, you would not get credit unless you showed your work. If you showed your work and you were off by a couple of cents, they'd give it to you. When it comes to the other things that they're looking for here, why didn't they lose points? The best thing to do is to actually look at the rubric itself, and this is what it says. The first section is about identifying that you're doing a 1 sample Z interval or a 1 proportion Z interval. And if you look over here, it says either by name or formula. So if you'd left the name off but you showed the formula, you would be okay. In later questions, they do dial down and get more specific with that. And in some years, they have specifically said if they didn't show the Z star, they don't get full credit. So it's year to year. What my expectations that I give to you are done in a way that for every single problem that has ever been shown, you would have gotten full credit. Because I can't always predict what they're looking for. So the first piece was the identifying what you're trying to do. And conditions. But notice that says what? Both. How many conditions do we actually have? We actually have 3 conditions, and our last one correctly identified all 3. Since this time, they have kind of revamped the grading requirements for the exam. And they have specifically specified, repetitively redundant, that you must address the 10% condition. They did not do it here because they were saying, well, you don't really know exactly how many people there are in order to check the 10%. Now they want references to the 10% condition so that they show that you are aware of that condition. And you have to have both of them. If you have identified the correct procedure but only got one of your conditions correctly, then you can still get a P. But that would drop your score down from a 4 to a 3. The next piece is about the correct interval. If you have your interval correct, full numbers, everything that you have rounded out absolutely correctly, you will get full point for that, full credit. If, however, you make one simple little calculation mistake, you do not get that point. Unless the response gives supporting work. If your supporting work is correct, and you have all the numbers in the right spots, and you just did a calculation wrong, you can still get a 4. You can still get a full credit for that. Because we're like, hey, you know the nature of what I'm trying to test you on. So you made a calculation error. Okay. You've shown me you know what you're doing. Questions on what I'm talking about so far? So correctly computing it. And if you look here, alternate appropriate supporting work must have the form. So you must show the proportion plus or minus the critical value. That's your C star. And either your standard error or standard deviation, whichever way you want to identify that. Okay. Then we had 2 more pieces, if I can figure out where they went. Here it is. Part 3 is doing an appropriate interpretation. Now, they do not say you have to have word for word my interpretation. But my interpretation covers everything that they want. Talking about a population proportion, which means the true proportion of all. That's what we get that from that. A clear understanding of the parameter, what that is. Context. That's in our interpretation. Mentions the 95% confidence and interprets it correctly using, we can be 95% confident or with 95% confidence. You see, that is over there for my interpretation. That interpretation ticks off each and every piece for my confidence interval. Okay, the blue, the pink, the green, all of that in that statement. And then from the last piece, section 4 is basically if you have the correct interval answer and you showed your work, you get your point. You have your correct answer, but you did not show the work, you get a P. Anybody have questions as to where the answer for the last piece came from? How, in fact, they got those numbers? Is everybody okay with that? Because they do that all of the time. You take your confidence interval, these are proportions, a proportion of the population, 3,000. So I took both of those endpoints, times it by 3,000. And then for each of those individuals, they lost 25 cents, so timesing it by 0.25. So based off of your answer, are you okay with what you did? You satisfied? What do you think you missed out on, other than me just not giving you enough time? Was this helpful, seeing somebody else's answers? Or would you rather just continue grading your own? Let me know. I take feedback. Would you like to do this again? Okay. Would you, for those of you who would not like to do it again, I don't really care because you probably don't want to work. Ha 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 ha. Just kidding. No, I want you guys to have the widest variety of ways to evaluate. Oh, don't give me that. Look at me like I've said something horrible. I haven't. I want to give you guys the most opportunities to kind of show your understanding here. All right. Hopefully this is charged enough to last the block. Okay. Yeah, go ahead. Yeah, go ahead. Make it quick. Did you have your hand up? Okay, that's fine. All right. Before we even get started, I want to kind of clarify something for you. Our chapter 20, we're not going to have just a quiz over just chapter 20. We're going to actually combine it with 21 because they're both kind of small things. So we will spend today and next class over chapter 20, but you are not going to have a quiz following that. Okay? Hopefully you all watch the videos because I'm not going to I really want to be able to describe what's going on today, and we are not going to have time for me to let you just copy everything down. All right? So what we're talking about today is the whole idea of connecting confidence intervals to hypothesis tests. Because really, they should always support each other. They should back each other up and come to the same decisions. And there are a lot of linking facts that go into that. So, about those intervals and those are hypothesis tests. The purpose of a confidence interval. Remember, a confidence interval is focused on the sample. Sorry, I assume that you can read my mind. Confidence interval is based on the sample. A hypothesis test is based on the parameter, population parameter. That's fine. No. And what we're looking at here is we're saying, okay, for a confidence interval, I'm starting with my sample. Does the hypothesis match it? Whereas a hypothesis test is I'm starting with the parameter. Does the sample match it? Do you see how they're going just two different directions? Where you start and where you end up. So a confidence interval should approximate a hypothesis test. And basically what that does is you are going to construct your confidence interval. If it was a hypothesis test, you would take that null hypothesis and you would say, does it fit in my interval? And we've done those. We did those when we were doing confidence intervals. We just didn't call it that. We didn't call it a hypothesis yet. And if the null fits into our confidence interval, then we would not be able to reject, because that means our confidence interval supports what we thought was originally true with no change. Okay? So you're asking yourself that question. Does the hypothesis fall within our confidence interval? And it's a very simple one, and that is the true relationship between a confidence interval and a hypothesis test. If you're inside, for your hypothesis inside your confidence interval, you would fail to reject. If it's outside, you would. Okay? But we have this little kind of wibbly-wobbly piece. And that is that every single one of our confidence intervals are two-sided. A two-sided confidence interval pairs up with what hypothesis test? Not equal to. And the reason why is because for our confidence interval, we're finding our two values. Those two values mark the start and end of our interval. And if we are inside that, we fail to reject. If we are outside of that, we reject. So a confidence interval has a direct relationship with the hypothesis test through alpha and your confidence level. And the relationship here is this. And this is very important. I'm going to write this down so you can kind of see where I get how I remember these things. I think of this as a two-sided test has the formula that alpha is 1 minus the confidence level as a decimal. Or you can look here, alpha as a percent is 100 minus your confidence level as a percent. Okay? Two-sided test, that's how we match up. So if I'm going to make a 90% confidence interval for a two-sided test, what would that pair up with for an alpha? Say it again. 0.1. 0.1. Because 90% is within here, that means that 0.1% or 0.1 or 10% falls outside. And if it falls anywhere in that outside part, we would reject the null. That's for a two-sided. One-sided is different. Because in one-sided, this is still my confidence interval. But for one-sided, it's not about falling in either of these pieces. It's about falling in one specific one. So think about this. If this was 90, we've already said that the outside part would be 10 or 0.1. This outside point is 10 or 0.1, but I was only looking for greater than. What would that match for an alpha level? 0.05 or 5%, because we're only looking at that half of it. That means when we are looking at our one-sided tests, we have to think a little bit more carefully. And when we have a one-sided test, you can either say 2 alpha is 1 minus the confidence level, or you can say alpha is half of 1 minus the confidence level. Those are the really big things for alpha and the confidence level. And these guys are questions that you're going to be faced with all the time. For a lot of times, they will say, all right, I want you to do a hypothesis test with an alpha of 0.05. And then the very last step is they'll say, determine the corresponding confidence interval. And you'll have to understand, depending upon whether my alternative was one-sided or two-sided, what then would my confidence level be based off of my alpha. Now, the reason why I wrote this down is I want you guys to see this. You see, both problems have alpha is 1 minus the confidence level. You guys see that? You're okay with that? Both sides have a 2 in it someplace. If the 2 is in your sides, it's in the title, it's not in the formula. You get what I'm talking about? 2's here, it's not here. If the 2 is not in the title, it is in the formula. Okay? That's really the only way I can remember it. Otherwise, I don't know. But if we're going to have a two-sided, you do not divide by 2 anywhere in here, or times by 2. If you have one-sided, depending upon what you're looking for, if you're looking for alpha, you will divide by 2. If you're looking for confidence level, you'll times by 2. Okay, so just remember that. There is a 2 in there someplace. Do you call it two-sided, or is there a 2 in the formula? Does that help a little bit? I'm always looking for things that kind of help jog your memory. And that is because, again, the confidence level will still, or confidence interval will still be marked off by that z to negative z. But for one-sided, we're only interested in half of that. So if this is 95, 95% is inside. What percent is outside? 5%. But how much am I going to reject for? 2.5%. Okay? So basically what we're going to do here is we're kind of taking a step back. We're just going to be doing our hypotheses and tying that to one or two-sided. And we're going to go through this pretty quickly. I'm not concerned about you writing this down. But when we're talking about a hypothesis, what do we need to do? What's the first thing we do when we do our hypotheses? P. And when it comes to your quizzes, which you guys got back, the most common mistake that I saw actually dealt with that defining your P from the very beginning. And that's because P is what does P represent? A proportion. I had people who said P was the number of women, or P is the number of businesses, or P is this. P is not a number. P is a proportion. And that is a very important distinction to make, because if you are talking about numbers counts, that's actually a completely different test. So you've got to be very careful with that if you say P is the number of, you are wrong. Okay? Be very careful with that. So if we're, go ahead and read through this problem. And let's talk about P. What would you define P as? Yeah, the proportion of computers that had a, warranty problem. Pretty straightforward and simple. So my null hypothesis is always that there is no change. So my null hypothesis would be that P is equal to 0.2. Good. My alternative, I want to improve that rate. So what should I see that rate do? Less than. Beautiful. And if it's less than, is it a one or two-sided test? One-sided test, which means we would be using these formulas for alpha if we're trying to tie them back and forth to each other. Read this one. By the way, we had a fun time trying to discuss how to pronounce that word. Philanthropic, yes. We had some very interesting philanthropic. It is philanthropic. Yeah. No, yes, it's philanthropic. Okay, so. What'd you say? Okay, sorry for dragging your brains off of the track. No! Not a clue. That's okay. I really don't. What is it? No. That's okay. Okay. Hi. Squirrel! Oh my God. Okay, guys. Shh, please. So for this problem, what would P represent? The proportion of people that responded to their request. Is that okay? P is the proportion of people that responded to their request for donations. and what they're establishing as responded to, whether it's like they said, oh, sorry, but I don't have money right now. I don't know if they call that a response or if they're looking at people who actually donated, so I probably wouldn't get too crazy with that. My null hypothesis would be that P is equal to 0.0475. I am notorious for screwing up where a decimal goes, because I just always want to put just the decimal in front of whatever the number is. So just be careful with that. And please forgive me when I do that over and over and over again. Just yell at me. It's okay. I'm used to it. The alternative, greater than, which makes this one or two-sided? One-sided. This is one-sided because the alternative that we're looking at here is greater than. This isn't a big leap, right? I mean, we talked about one and two-sided with our null hypothesis. So, yeah, this is pretty good. Next one. Very, very, very common type of stats test. Bless you. The ultimate question. Pepsi or Coke? Diet or regular? You cause cancer. Some things do. And it's not a cause because they haven't done an actual experiment on it. It's an observational study. I don't think I've ever heard someone say that. Depends on where you live. All right, ladies and gentlemen. Hey, guys. Folks. This problem is good for multiple reasons. One of the primary reasons why this is a good question, there are no numbers there. What did you just say? 50-50. Because for this, let's just first pick P. What is P going to represent? Okay, and it doesn't really matter which one you pick. You just commit to one. So P would be the proportion of people who, or proportion of students who prefer Coke. What would my alternative be? Not equal to. Because there are no numbers in here, really what we're looking at. Remember, our null hypothesis is always that there is no change, or there is no difference. If the two proportions are equal, that means they would have to be 0.5. Do not get that confused with an alpha of 0.05, which you default to if nothing's stated, or a confidence level of 95 if there's nothing else stated. Okay, there's a reason we chose that 0.5. And because if there really is no difference, it's a 50-50 shot as to whether they prefer Coke or they prefer Pepsi. Okay? The alternative here would be what? Not equal to. Why? Yeah. We're not like placing value of one or the other. We're not in Georgia and saying everybody believes Coke's better. Or I don't know where the New Jersey plant is, so New Jersey. No, someone was saying the Pepsi plant was in New Jersey. That's why the word New Jersey came out of my. Anyways, we're moving on. Miranda. No, I am odd. It's okay. Well, if you, and it's really, really interesting. A lot of people don't understand, but Pepsi and Coke are very similar. And it is a very, very common test to see blindfolded sample. Well, you don't really need to be blindfolded, but a study where you would test, can you pick out of these two whether it is Pepsi or can you correctly identify them? You did that. You did that with your mom? And some people can tell and some people can't, but we're looking at that percentage. Is it 50-50 or not? So, careful, guys. And with that Pepsi versus Cola challenge, there are a whole spectrum of sample type things that you can do. You can actually go to Atlanta and visit the Coca-Cola Museum. And they have regular Coke from around the globe. It's kind of creepy. Talk about proper product placement. Anyways, guys. The reason why you do that is because in each of these different countries, they actually structure the taste a little bit differently. And so a lot of people, and one of the greatest differences is between the Asian market and the Western market. Very, very different flavors in their Coke products. So these types of tests are very important to those types of public relations people. And here we've got that same idea, but we're kind of narrowing in a little bit more. Even though you might think that the goal is to appeal to the most people. Everybody likes Coke. Everybody should drink Coke over Pepsi, or everybody loves Pepsi. If you go to a drive-thru, do you order a Coke or a Pepsi? Depending upon where you are, things can be different. It's also true when you're talking about the specific types. When you're talking, a lot of them, about the diet sodas. Diet sodas are more, what's that called? Promoted or set or geared towards an older group, because they figure those are the folks that are worried about their caloric intake or their sugar. Okay? But let's say that they want to conduct a test whether to look at Diet Coke versus Diet Pepsi. And a lot of people say you might not be able to tell the truth between the regulars, but you can definitely tell the truth between the diets, because they use different types of sugars. So if I'm looking at this, what would the null hypothesis be for A? What would P be? P is equal to, but what does it represent? What does P represent? Right, and it's you can't say Diet Coke or Pepsi. You really have to pick one of them, and that's a very important thing. You cannot just say the proportion of people who prefer Diet Coke or Diet Pepsi, because if you put it that way, then you're saying those two over everything else. If you're looking at just those two, you have to pick one and commit to it. So the null hypothesis I did here was P equals 0.5. What would your alternative be? Not equal to, because we're not looking from one of those companies' perspectives. Okay, now we're going for PepsiCo. PepsiCo is the company, believe it or not, that makes Pepsi. Gasp in awe. And they're trying to appeal to teenagers. And we're looking at an original formula versus a new formula. What would P be? And you can commit to either one of those. But this is why we have to define P before we go anywhere. Because depending upon how you define P in this case, your alternative is completely different. So if we define P as the proportion of teenagers who prefer the new formula, my alternative hypothesis would be what? Greater than, because we want that rate to increase. If my null hypothesis, my P, was the proportion of people who prefer the original, what would my alternative be? Less than. So it's why it's so important to identify your P. In either case, both of those are what kind of tests? One-sided. Okay, so far so good? Okay. Try to read through these two, discuss. Let's just go straight to the one or two-sided. Yes. What do you think for C? One or two-sided? One. Why? My alternative, for example, if I said P is the proportion of people who are in favor of passing the budget, you would say, one more time, greater than. And I'm just going to tell you that there are some schools of thought that will say your null hypothesis, if this is your alternative, if your alternative is greater than, then your null should be less than or equal to everything else. There are a lot of people who will argue one way or the other, but the truth is it's not going to affect our calculations. So we take the path of least resistance. We just take the equal to for the null. If you were to say that the null is less than or equal to 2/3 and this was greater than, I would not mark you wrong. Okay? Just making sure that you're all right with that. What about D? It's two-sided. Why? Goes up or down. So it means my alternative would be not equal to. what would my P be in this case? P is the probability that and thank you for committing. You have to say that. You cannot say the probability the stock market will go up or down. Because that would mean P is the probability that you have any change at all. We're specifically looking at one direction because we want those to be pretty balanced. And the truth of the matter is, it is very rare for your stock market to stay exactly the same. So we're not really looking at the equal. We're looking for that up or down portion. Okay, and so that is two-sided. Okay. I really like where we are in this course, because we're finally getting to a point where we see, why do we do statistics? And it's boom, 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 you always follow these steps. But even with this, there is still that area of interpretation and critical thinking. And from day one, that has been the whole class, the whole country taking AP statistics. That is everybody's biggest weakness. Because critical thinking is a skill that's very difficult to teach. You only really get it by doing it. Okay? So what happens with statistics, and this is a huge criticism against it, is you can do all of your tests and all of your studies perfectly. No question on your methods or the records that you kept. You did it beautifully. And you're still wrong. It's because that idea, I feel like I've got a musical background going to this. I don't know what it is. But the problem with this is this idea of natural sampling variability. You're going to have weird samples. Your samples, even if you're 100% random, might not reflect the population, no matter how careful you are. It's going to happen. Hello, the last election. All of the polls pretty much said that Hillary was above Donald Trump. But that's not the way it worked. That doesn't mean that they went about the polling wrong. It just means that even a little bit of variability in a case that close, you can come up with the wrong conclusion. All right? So, when we perform a hypothesis test, we can actually be wrong in two different ways. And these are very, very important. Hopefully you wrote this down from the video. The first way is by making a type 1 error. And, okay, this is really bugging me. Give me 1 second. All right. So if the null hypothesis is true, now, ladies and gentlemen, when we talk about the null hypothesis, we're talking about the idea that there is no change. So I love this example, the idea of a pregnancy test. The null hypothesis for a pregnancy test is that there is no change. And the no change status is that you are not pregnant. You have to change to become pregnant. A change has to occur. So a type 1 error is where we say that the null hypothesis is true. There is no change, but we claim otherwise, which is why I love this. Imagine being that man in a doctor's office, did the urine analysis simply because they do that. And he comes back and says, you're pregnant. As of right now, if you are biologically male, that will not happen. Unless you're a seahorse. Okay, that's very good. Wow, that came out of the blue. But does it ever happen? Do you think there is ever a time when a man will take a pregnancy test and it comes back positive? It is. It is a possibility. And gentlemen, for your safety, if you take a pregnancy test and it comes back positive, get yourself to the nearest doctor ASAP. And I'm not saying that this is an STD. Yeah, it's a different changes in your hormones level can be indicative of many really bad things, including cancer. Yes. So guys, are called your false positives. They have them for the flu test. I really don't have a flu, but I took a test and it said that I did. You have certain things that just kind of pop up, like chicken pox. That is a false positive. That means I have rejected the null, but I shouldn't. That is your type 1 error. I have problems memorizing things. But if I can picture this, if I can remember that the pregnant man is the type 1 error, I tend to make fewer mistakes. Then the other error, which is the type 2 error. The type 2 error is the woman who comes waddling in to the emergency room because she feels like she's about to give birth. Her water has broken. And the doctor says, oh, no, you're not pregnant. You've made a mistake because you're telling me that there has been no change in her status when there actually has. So that's saying that we've kept the null, but we should have rejected it. So that is your lady where you can actually see the footprint every once in a while on her tummy. It's really weird. That's very strange. Yes. But that is, guys, that is a type 2 error. That means we have those two different ways to be wrong. Now, what is the most important thing that you understand from this chapter is this. Okay? This is the relationship between null and alternative hypotheses, your decision, being correct, being incorrect, and level of significance, which we call our alpha, and what we call the power of a test. So we know that no matter what, the truth about the population is going to be set. You don't really have control over that. Do you understand what I'm talking about? I do not have a say in whether or not my null hypothesis is true. That is going to be something mysteriously true that I haven't figured out. So this line is not moving. Okay, the actual truth is not moving. I just don't happen to know where it is. My decision becomes to reject or fail to reject. And that is based off of how big I make my alpha. Does that make sense? So I can't really control where I move this line because I can't control whether the null is true or not. It just is. But I can control how big I make my alpha. If I want to cut back on the chance of making a type 1 error, the pregnant man, and I make alpha smaller, does that mean if my null is true, my correct conclusion gets bigger or smaller? If I make this line move up, what is that going to do? That's going to, making alpha smaller will make the correct conclusion, if the null hypothesis is actually true, happen more often. Making alpha smaller, if I'm actually trying to reject the null, if the null hypothesis isn't true, is going to reduce that. So when we make alpha smaller, we're actually cutting back what's called the power of the test. Because our whole purpose of any of these tests, of a flu test, a pregnancy test, an SAT, an AP exam, the purpose of all of those is to correctly reject a false null. To catch it if somebody is pregnant. To catch it if you have the flu. To catch it if you've actually learned what you're supposed to learn. That is the goal of those tests. That's why we call that the power. But making alpha smaller, yes, can increase the chances of a correct conclusion if the null is true, but it decreases it if the null is false. Does that make sense? This is all linked. If I shrink alpha, I grow these bottom two boxes. If I make alpha bigger, I grow the top two boxes. And it is a trade-off. It is a balancing effect between the two. Okay? Now, I'll come back to a little illustration with this in a second. But first, I want to kind of think about this situation. This is in your notes, by the way. So we're in your notes on this one. I want you guys to write the company's null and alternative hypothesis. And then we'll go through the errors together. Yeah. All right, what does P represent? The proportion of defective chips. Computer chips, not potato chips. Everybody okay with that? The null hypothesis would be that P is equal to 0.08, and the alternative that it is less than. Because if P is a defective thing, and I want to reduce my defectives, that means to decrease it. You have the opportunity to, if you say you wanted to identify P to be the proportion of chips that had no problems, you can do that. You just have to be very, very careful as you go through your work. So for us, we're going to set P to be the proportion of defective chips. Now, we've got to think very carefully here. And to me, this is one of the hardest aspects of hypothesis tests and confidence intervals. And that is identifying an error in context and talking about the impact. So we've got here a question for a type 1 error. Notice the type 1 error is when the null hypothesis was true, there was no change, but you rejected that. So what was true in this case? So the type 1 error is when the defective rate is, in fact, 8%. There's been no change. But what do? We say that there is a change. So what's actually happened is my defective rate has not moved, but I claim it has. If I claim it has moved, what do you think I would do? I would keep the program. I would offer more incentives. Why might that be a bad thing? You're losing money. You're throwing money at something that's not actually changing anything. Do you understand what I'm talking about there? The type 1 error in this case is negative for the management company because they're spending money on something that's actually not benefiting them. Okay, type 2 error. If we look over here, a type 2 error is when the null hypothesis is false. There actually was a change, but we did not reject it. So in this case, what would be true? The defect rate actually did reduce, but we said it didn't. Why is that a negative? What I'm hearing, I'm thinking is correct, which is very quiet. One more time. They'll stop the program, and they'll miss out on the chance to reduce their rate. The rate will go back to normal. Now, depending upon what your point of view is, one of those may be worse than the other. Have you ever heard of a cost-benefit analysis? It's partially based in this idea of, from your perspective, which is worse. Is it worse? And this is how people determine what alpha is the best. Is it worse to make a type 1 error where you say that there has been is when there was no change, but you say there was, so you're throwing money at something that doesn't actually do it. Is that good for anybody? Employees would like that. Yay! Incentives! I can get more money! Woohoo! Who's that bad for? The owner, the one that's actually giving the money, whatever that program is. Whereas a type 2 error is going to be bad for whom? Worse, I guess. The workers, the employees, or the customers who actually get the chips themselves, whether they're defective. But, hey, it'll save the owners some money. So it's a very delicate balance. And this, I'm hoping that you see with this that it is not necessarily the test that's difficult. It's the interpretations, and what's going to happen from here on out is you're typically going to be asked, for example, explain a type 1 error in this case and its implications. Or you'll be asked, what is the connection between your type 1 error, between your hypothesis test and your confidence level? Or they'll say, here's your confidence level. Now, what would the test give you? So you've got to be able to move through all of these things, and that requires a really strong understanding. Okay. So you guys have in front of you problems 4, 5, and 6, so please go ahead and do those. Yay, the never-ending sniffle season. Four, 5, and 6, please. Can I move on to the next slide? You still writing this? No? Okay. I didn't hear any yeses. Were you still writing it? I can go back. I'll go back. I'm sorry? No, when we're going to interpret an interval, that's the top one. Okay. So I have created a confidence interval. By the way, if my confidence interval was from 5% to 7%, what was my observed statistic? Why is it 6%? Because where is that? That is considered to be the middle. The middle of your confidence interval is what you would have seen. So if I gave you a confidence interval that went from 5% to 7%, I could actually calculate everything based off of that. I can say, hey, my p hat here would have been 0.06, because that is smack dab in the middle of it. And if I know my p hat, and I know my confidence interval, I can actually go back and even calculate what sample size was used. So we can do all of those things. But if this is my confidence interval, and what was my p, my null hypothesis? 8%. What would you do? What would we conclude? That it's effective. Why would we conclude that it's effective? Right, because my alternative hypothesis here would have been less than, right? That we're lowering the rates. And it just so happens that my entire interval qualifies as less than. And it has to be the entire interval that fits whatever we're talking about. It's not just one value in the interval, but the entire thing. So for this case, because the entire interval is below that 8%, or we can say the interval does not contain 8%, then that means that we have evidence to suggest that it actually has helped. The incentive program is leading us in the direction that we want to use. Now, I made a 95% confidence interval. I want to determine the alpha. Before I can determine the alpha, what do I need to make sure I identify? Whether it's one or two-sided. What is this? It is one-sided. So could you tell me, I've erased my formula, could you tell me what level of significance we used? No. Yeah, remember, one-sided, the 2's in the formula. So you're always going to do the 100 minus 95, always, or 1 minus 0.95. Always going to do that. It's two-sided, that's it. One-sided, you've got to divide by 2. So for this problem, they used an alpha of 0.025, or you can say a 2.5% significance level. Okay? All right with this? Okay. So my alpha that I used was 2.5. I'm going to change that to 1. What have I done to my alpha? I've shrunk it. I've made it smaller. I've decreased my alpha. So if we go back, we want to think about that table that I showed you. It's very important. If I go back to this, If I make my alpha smaller, okay, looking at all of those relationships, alpha is smaller, then that means what? Give me an advantage to making alpha smaller. It is increasing the confidence, yes. Because instead of having a 95% confidence interval, if my alpha is now 1, what is the confidence level? 98. Okay? But what does that actually do for my decision making? It increases the type 1 error, which means it'll increase the chance that I actually fail to catch when a change has occurred. So if I want to talk about power, if I decrease alpha, what does that do to the power? One more time. It decreases your power. Okay, remember I'm talking about alpha moves that line vertically? And the power of a test is all about correctly rejecting a false null, making a good decision to say that change has occurred. So advantage would be that you're more likely to reject the null if it wasn't true. Like if it was just some little thing that, yay, people got happy, it worked. Not really. It reduces your risk of wasting money. But as a disadvantage, you wouldn't be as powerful. You wouldn't be able to catch when that program is actually doing what it's supposed to do. You see what I'm talking about for linkage of all this stuff? I think power of a test is one of the hardest things to understand, simply because it's very difficult to kind of picture what's going on. So I've got for us an app. Okay, and actually let's do this. Let's center this since we're talking about proportions. We're going to center this at 0.5. And we're going to make my sigma be, let's say, 0.5 also. Okay? So that's going to be a proportion. This guy up on top, this is the distribution of your sampling. Yeah? Type 1 is if we decrease our alpha, then what you're doing is you're making your type 1, the type 1 error is the one right below it, makes that bigger. Okay, it's going to actually make this guy smaller. Less likely that you fail to reject. Okay? So if we're looking here, for this case, we're saying that the truth of the population is 0.5, so my distribution is centered there. And when we're talking about a sampling distribution, we find the standard deviation by saying root PQ over n. So I've put in my theta that works for this, and then this is my n. And changing my alpha will change different things. This down here is saying, okay, let's say my sample actually said 0.314. But instead of 50%, I had 0.314. Okay with what I'm talking about there? That's what I'm talking about. This is my sample. The power of the test is the difference between this is my set alpha and over. This is the power of the test. Anything that falls in here is going to be when I would correctly reject the null. Okay, it's a kind of a really delicate thing. And if I increase alpha, I'm sorry, am I making alpha bigger or smaller? So I'm decreasing alpha here. What's happening to that red error? It's getting smaller. If I make alpha bigger, what's happening to the red area? Getting bigger. So if I increase alpha, I increase the probability of correctly rejecting the null. It's increasing the power. And let me even make this a little bit closer. Let's say it was actually 0.45. Center them closer. Okay? So again, if I change my alpha, So this is making my alpha super small. A super small alpha doesn't have much power. The bigger my alpha gets, that's the standard. The bigger the alpha gets, the more powerful that we are. But we can also make other changes here. I cannot change what's true about the population. I cannot change its standard deviation. My sample is going to be what my sample is going to be, but I can change my sample size. This is a sample of size 50. What do you think a sample of size 5 is going to do to your graphs? Are they going to get taller, shorter, skinnier, fatter? What's going to happen? Gets a little bit fatter. It comes down a little bit on the top and it comes in on the sides. That's a sample of size 5. Sample of size 10. You see how it's scooching in a little bit? 15 scooches in a little bit. 25 scooches in a little bit. What's happening to this red piece? It's getting bigger. That red piece, when I change my sample size, that red piece gets larger. So I can change that red piece by either changing my alpha. And if I might want my red piece to be bigger, do I want alpha to be bigger or smaller? You can increase your alpha, or to make the red piece bigger, you can increase your sample size. Okay? And calculating the power of a test is not something that you're going to be doing in this class because you have to know what the actual truth is. And the purpose of taking a sample is to kind of guess what the truth is. If I knew what it was, I wouldn't do it. But that might be something you calculate in a later class. But if we think about this, if I decided to change my incentive program from studying just 1 month to now I'm going to study 3 months, what is that changing in the whole shape set spread? Going to change the shape? What do we describe shape as? Assumptions and conditions met, we get to use normal model. Is it going to change where the center is? Because it should be centered at P. Does it change the spread? The spread, how do you calculate sigma? Root PQ over N. So if I'm going from a 1 month trial to a 3 month trial, I'm changing N and making it bigger. If I make N bigger, what is that doing to the standard deviation? Making it smaller. And bigger is always better. So if I increase the sample size, what's going to happen to my power? The power is going to increase. Okay? The big thing that I need you to understand about power is in order to gain more power, you either need to do what to the alpha, increase alpha, or do what to the sample size? Increase. Read over number 8. Talk to each other. What do you think? So we originally had a P of 0.08 or 8%. After this incentive program, now I have a 6% defective rate. And we've said that that is significant. And when we use the term significant, we're usually saying statistically significant. Yes, I'm very certain there has been a change. Why would I not stick with the incentive program? I can't hear you. And that's too expensive. There you go. Sorry, that's what I was looking for. It costs too much. It's like, there's your cost-benefit analysis. How much does it cost to get the return that you're getting? Is it worth it? If the program costs $1 million, but you're only saving $500 in defective chips, is it really worth it? Probably not. And that's why statistics plays a really strong role in our decision-making process. Okay. All right, so we're not going to have time to get through this problem, but I will make sure that we get to it. It's just not going to happen today. Yes, I will. I will. So, just so you guys know, you do have a Chapter 20 My Math Lab assignment. It is not going to be due the day of the quiz because the quiz is going to be combined with the Chapter 21. So that means it's going to be due, the next time I will see you is Wednesday and then Friday. So this is going to be due Thursday night before that second class from now. Does that make sense? Okay. And your quiz is going to be in 4 classes. But I don't want to give you a double load of homework for one night because I know you will wait till the last minute to do twice as much. Not a good idea.